going to stop with, what's the last one? 4, yeah. Yeah. Okay, so now when it goes to turn this, when we go to turn this into sigma notation, which if you're a good student, you just already did this like 5 minutes ago while I was rambling about other things. What do we get when we go to turn it into sigma notation? Actually, there's a couple different ways. Yeah, there's going to be a 2/5 in there.
Times summation I equals 0 to 4.
Yeah.
F of 2I over 5, or 2/5 I.
Okay, so yeah, so there's like 2 ways to do this. We do this as a sum from 0 to 4 of, this is what, yeah, I'll say, what was it again? And then it's just like f of I times 2/5, right? Yeah. Okay, that's fine. The problem is, this is correct, so I'll put happy face. And then I'm also about to cross it out, because I don't want to do this, because it just gets kind of annoying when you sometimes start counting from 0 and sometimes start counting from 1. We have all these happy formulas, and all the happy formulas start at 1. And so, therefore, in order to like be consistent, because manipulating indices is kind of like difficult,
So
I want to not
just-
do it this way.
So why can't we just start over?
We can. We can, but upon the penalty of like slightly more annoying formula, right? Because if we start at 1 and go to 5, then what happens, Calvin?
2/5 times I minus 1.
Yeah. Yeah, so that's pretty much what happens, right? Because now the first rectangle is going to have like a 0 over here. The second rectangle is always going to be like that one. You guys with me? It's like not that. People who like do programming, this is like just like baby stuff. Okay, good. So everything's fine, except now when we actually plug it in, it's just more tedious algebra, right? But I think we can handle it. What's it going to be? You guys see what I'm talking about when I say more tedious algebra? Tedious / awesome. I don't know. What? Yeah, you can also do other little things. We're not really worried about efficiency here. We're just sort of like practicing stuff. It's more actually all about the setup and the thinking than it is about the actual doing it. But we're going to do it anyway. So if I do this, then this is going to be, I guess I need to square it, right? So it's like negative, well, that squared, whatever that is. Ugh. Plus 5. Follow? Same with me? Okay, then we can just keep going. So this is 2/5 sum. Keep going, try to stay ahead of me. Maybe I'll just like one more thing. You guys did that right? Did you get that? Yes? Okay, now I need to split it up into like 3 sigmas, right? Kendall, you cool? Just doing like arithmetic and algebra 1 and stuff. I think Amit is doing it correctly. Squares. Yeah.
12.3.
No.
Wait, what?
No.
25 minus 4/5.
Oh yeah, 121 over 25.
Yeah, wait, what's 5 minus 4 25ths? Sorry.
It's 125 over 25 minus 4 over 25, so 121 over 20.
121 over 25. Yeah, but then there's like another one times 2.
Times 2. That's 240.
Oh yeah, so it's
242 over 1.
minus 242 over 125. It's not necessarily the best way to do this, but that works. I think I did that right with heat itself. Yeah, 125 minus 4, 121 times 2, 241. Yeah, cool. All right, and now you just plug them all into the formulas. Get a number. Tell me what you get.
Ethan, there's like a random just like so weird.
I think I feel like we'll need them. I'm gonna go to the top. This is the margin. 48. I used up like all that space.
Open up and go kill.
Oh, we're doing this right.
Negative 242 over 125. 121 over 25.
So it's like
Why is it negative?
Why is it?
Oh, it should be positive. Yeah, why is 242 over 125?
oh, it should be plus, right? I don't know. You said so, right? 5 minus 4 25ths is 121 over 25 times 2. Yeah. So, or do it however you want. I mean, just see if we get the same thing. Plus. Yeah, I got that. That's like minus 4. Did you get? Yeah, that's right. Yeah. 202 over 25. Right now you got that, either by doing it my way or your own way or whatever. Okay, I'm fully confident that you all could, if you needed to, get that right. It's just a matter of cranking which one. Okay? All right. 202 over 25 is like 6. It's 6. No, it's 8. It's 8. And 2 25ths is 8.08. All right. So I am now going to boldly proclaim that the true area under this curve lies somewhere in between 6.48 and 8.08. Agreed?
Yes.
All right, so a couple things. One, I've decided that LRAM is kind of a drag because of this. If I insist on starting my summations with 1, which I like semi-do because it just keeps things easy, then do you guys kind of appreciate how LRAM is kind of a drag because of this, where RRAM is like nicer? Okay. And then there's like another sort of obvious and common sense thing to say now. I mean, like, are you happy with this estimate? No.
I don't really get what the point. Yeah, like I don't really
what's the
get what
point?
the point is if you're just not even gonna exist.
Oh, well, we are going to get the answer. It's just rounded to the nearest like 1.5, which is like not that good. How can we do better? Class, how can we do better?
More rectangles.
Yeah, more rectangles. More rectangles. Steven, how many rectangles would you like?
Wait, does it involve a calculator?
Wait, hold on. How many rectangles do you like, Steven? Steven would like 6. Can someone else be a little bit more bold?
16. 7. No.
7. I heard 7. 16. 8. I heard 1,000. Keep going. 4 million. Yeah, there we go. Now we're talking. So calculus class are both useless. Say it again.
Infinity rectangle.
Yeah, the rest of you are dreaming too small. I want infinity rectangles. Why not? All right, so I am going to. Right, so I'm going to skip pages 2 and 3 because they're annoying, and I'm just going to go to page 4. You should try it on your own. They did it in the other classes, but I don't feel like it. On pages 2 and 3, I do this problem, but I do it with LRAM, and LRAM is annoying. Let's just do it with RRAM.
Okay.
All right, so Mateo.
Yes.
But you kind of need to read page 2 for a minute so you know what function we're talking about. The function we're talking about is the function y equals x squared plus 1. Yeah, but pages 2, 3, and 4 are all the same problem. Pages 2 and 3 is doing the problem in the hard way with LRAM, and page 4 is doing the problem the easy way with RRAM. We're going to just do page 4. So the problem is y equals x squared plus 1 from x equals 1 to x equals 4, and go.
Wait, what?
Oh, maybe I should give you a little bit more guidance here. Okay, so here's, let's see, here's 1, 2, so here's like 4. When I plug in 1, what is this function again? X squared plus 1. When I plug in 1, what did I get? 2. Oh, is there a y-axis? There is a y-axis.
Those are 1 to 4.
When I plug in 1, I get 2, right? And when I plug in 4, I get 17. Thank you, Calvin. So I have like a sort of happy parabola, looks something like this. Cool? So cool.
Cool.
Okay, so we are now going to use RRAM, which is going to provide an underestimate or overestimate? Overestimate, yeah. So the first thing we're gonna do is we're gonna use RRAM. Why are we gonna use RRAM? Because we just decided that because it's easier. And the other thing is that how many rectangles are we going to use?
Infinity.
Yeah, we want to use infinity, but because you can't what the hell is that, right? Yeah, Kirsten's like, what? Suddenly we're just doing whatever the hell we want? Right. So what we're actually going to do is we're going to say that there are n rectangles. And then we're going to let n be as large as we wish. So answer, the number of rectangles is n. Okay. Now that we have let the number of rectangles